Okay, today we're going to start one of the most powerful forms of proof, and maybe the only one anyone here has ever actually done before in a previous class. And it's what's called proof by induction. Now, for most folks, this is probably their favorite version because it's purely algebraic. And it's one of these kind of problems that if you're doing it correctly, it just sort of flows. You've had math classes where if you start the problem correctly, you just, well, then this gives me this gives me this, and hey, I'm done. And it's this kind of thing. Induction proofs mostly are on formulas. Okay, I'm trying to show a formula is valid. So what we've been doing is taking individual statements and saying, show this quantity is divisible by 2, or determine if this is an odd or an even number. In other words, we're taking very specific things and either trying to prove or disprove. Now we want to take entire formulas and show that the formula is correct. Because there's a lot of formulas that you're told, and they're probably correct, but you've never seen the derivation for them. Okay, so that is kind of an issue. So the way proof by induction works kind of simply is I make a grand assumption. I make the assumption that the formula is always true for an arbitrary value of n. Okay, and n of course is going to be 1, 2, 3, 4, 5, that sort of thing. I assume the formula is true for an arbitrary value of n, and then I show that assumption leads to it must be then true for one more than that. So if I assume the formula is true, let's say for a particular number, 10, then I would show that it's true for 11 based on that assumption. And that seems kind of cheating, but if I can show at any particular point the formula is true by simply assuming that the previous step was true, then that would guarantee the next step and the next step and the next step. But there must be a first step too. So what I have to start with is prove it's true for the very first step, then show that this assumption. So it actually has two forms. The first one is easy. Okay, so let's suppose a formula states it is true for all n greater than or equal to a certain number. Most of the time that number is probably going to be a 1. Sometimes that number is probably going to be a 0. Okay, so there's two parts. The first step I do is I show it's true for n equals the very first possible number it could be. And a lot of textbooks will actually say prove it's true for n equal 1, but your formula might not start until 2, or it might start at 0. So you see there's a problem. It's just whatever the first instance of my formula is. And then secondly, I assume it is true for n equals some arbitrary value of k being an integer, in the future, in other words. The first two steps are generally trivial. I'm just stating something. And then the last step, the most important step, is then prove that my formula is true for n equals k plus 1. I'm assuming it's true for n equal k, and I'm showing that assumption leads to the following. I don't get to assume the final thing. I have to prove the final thing. But then that would mean if it's true for the first instance, then it's true for the next instance, right? One more. But if it's true for that one, then it's true for one more than that one. You see what I mean? And so on and so on and so on. And now we've guaranteed a formula is true forever. You saw that's kind of crazy, right? But it's not. It's actually not that complicated. So let's take a problem that we looked at. We looked at this one last day. We said if I take the sum from I equals 1 to n of I, right, we've got n plus 1 over 2. I showed that one. That was little Carl Friedrich Gauss's conclusion. Okay? You remember this one? This was an arithmetic series where we basically just add the first and last and divide by 2, in a sense. Okay? What's the first number? Well, this is 1 plus 2 plus 3 plus 4. So what this is 1 plus 2 plus 3 plus n. I am claiming that this formula is true. Now I know this formula is true because I've derived it a different way. I want to use induction now to prove that this is true. Just to give you an idea. This is actually a fairly simple proof. Okay? But we need to know when we are done and what we need to do. Now, in most proofs, you have to assume something. Sometimes I'll just say, does this equal this? And you can carry it through and see it's true. But in an if-then, which is a lot of times we're working with conditionals. If I said, prove if P, then Q. Or in other words, prove P implies Q. Can I start by assuming Q? No, and unfortunately that's what some of us are doing on our proofs. We're starting by assuming what I'm trying to prove. By the way, if you start any proof by assuming what you're trying to prove, don't write anything else, because you are completely finished. You started by assuming the conclusion. Nothing you write can help that. I'm not joking. I want to prove the following statement is true, so I'll assume it's true. Well, I'm done. So if I'm doing that one, the final statement what I'm trying to prove should be the last statement of my proof. Therefore, Q. That's how a proof should end. Now, if I'm trying to show P implies Q, then I have to assume P is the law. P is not only true, P is absolute. P cannot be questioned. So I suppose P is true. And my last statement should be, therefore, Q is true. Right, that's sort of the basic. Some of us are going a little too fast on the proofs. We're not even assuming anything. We're proving Q without any assumption. And by the way, Q is not true. It's absolutely 100% guaranteed not true without the assumption of P being true. But a lot of times we're leaving that part out. That's kind of critical. So do I get to assume anything here? There is one part of this problem that I will assume. It's step 2. So this formula starts at 1. So the first case I'm going to show is 1. And how do I do that? The sum from I equals 1 to 1 of I is what? It's only one number. It's just 1, isn't it? Do you all agree that's just 1? Well, according to this formula, it's supposed to be what? 1, because n is 1. 1 times 1 plus 1 all over 2. And what does that equal? That equals 1. Is that a good thing? Yes, that's a great thing. What if that didn't equal 1?
That's a counterexample. Right there.
Yeah, you're both right. I can stop right there. It means the formula is incorrect. If it doesn't work for even the very first number, then why would I bother continuing? Is that going to happen? Are you ever going to run into that? Probably not, because the whole point of this is to take something that we already know. I know this formula, I just don't know where it came from. I don't know, how to justify it. Most formulas we know, right? We can just plug in numbers and see that it works. Let's take something like the quadratic formula in algebra. You know it works, and when you're factoring a quadratic, you can use that, right? But did you ever see its derivation? I mean, you should have in an intermediate algebra class. Most of us forgot how it was derived, but it was derived. It wasn't just handed to you. But let's suppose it was just handed to you. You keep using it over and over and over again, and it seems to always work. And in math, sometimes that's okay, but I'd rather see where it came from. Now, I showed you where this came from yesterday. But what if you had never seen that? What if you were absent yesterday? Can I still prove this is valid by induction? Yes. So I've shown it's true in the first case, which is critical. This is easy. This is never hard. Because I started the sum at 1, 1 is the first case. Most of the time, the induction proofs are going to be on summations or products, the capital pi. And all you have to do is look at what's the first case. Am I starting at 1? Am I starting at 2? Am I starting at 0? Doesn't matter. That's my first case. So now step 2, which is fairly simple, we will suppose it is true for n equals k. So now I need to state this. I'm actually going to state what does this mean. This is what I'm going to do. Almost think of this as parenthetic. Okay, I'm going to suppose what? Go back to here. I'm going to suppose that the sum from I equals 1 to k of I is what? K times k plus 1 over 2. I'm going to suppose and assuming the same thing. I'm going to assume that this statement is absolutely true. It may be true, it may not be true. If it's not true, I will not be able to show that this leads to k plus 1 being true. If it's not true, I can't prove it's true. That's impossible. So, step 3, I now need to show it's true for n equals k plus 1. Okay? Well, if I take my summation, let me ask you a question. True or false?
True.
If I am assuming that this is true, that isn't showing up yet. But if I said, what's the sum of the first k plus 1 terms, isn't it the sum of the first k terms plus the k plus first term? Yeah, that's really not complicated. And what's the k plus first term? K plus 1. What's the 10th term? 10. What's the 100th term? 100. So do you agree with this statement? This statement is true with or without this, by the way. But now that I've assumed that, let's keep going. That means that this is equal to k times k plus 1 over 2 plus k plus 1. Now we roll up our sleeves and we do some algebra. Okay? I proved it's true for the first case. I assume it's true in general for any arbitrary value of k. Now, I'm assuming that that is true, so I can replace that sum with that quantity. But the sum of the first k plus 1 is the sum of the first k plus the k plus 1 term. Now let's manipulate this algebraically. Is there an easy way to do that? Well, what if I factor out? I can distribute, but that's a lot of extra work. I guess I could put everything over a common denominator, right? That'd be k squared plus k plus 2k plus 2. Is everybody okay with that? Is that what I would get if I put everything over a common denominator? Multiply top and bottom by 2, I distributed. Okay, well, let's keep going. That looks like k squared plus 3k plus 2 over 2, which is what? That would be k plus 1 times k plus 2 over 2. Is this a good thing? Go back to the formula. If I replaced n with k plus 1, what should this formula look like? Shouldn't it look like k plus 1, k plus 2? Does everyone see that? So is this exactly the form of the original formula if n equals k plus 1? Yes. Therefore, I am finished. This is a huge part of the problems. Everything we've done is true and correct, but sometimes we're working on, now, when am I done? What is my ultimate goal? So now let me go backwards a little bit. I'm trying to prove the truth of this statement. I assume it's always true for n equal k. So if I'm proving that this assumption leads to the truth of n equal k plus 1, what does the formula look like if I had replaced n with k plus 1? So what a lot of folks will do is sort of off to the side, I'll say, okay, off to the side, if I do this, then I need a formula that looks like this in the end. Because I'm now replacing n with k plus 1. This is what I'm needing as the last step of my problem. I can think of this before I even start, can't I? Now, I can't start with this. I can't assume this. Again, you can never in any conceivable context assume what you're trying to prove is true. Because you could take infinitely many false statements and make them true because you assume they're true. I'm going to assume that 1 equals 2. Now, from there, I can prove all sorts of things, but they won't be valid. Again, the only assumption in the problem is this. But notice what it led to. It led to the truth of the next step, which means that it would now be true for k plus 2, and then k plus 3, and then k plus 4. And since we already showed it was true in the first case, that means it's true in the second case, and the third, and the fourth, and the fifth. That's what induction does for you. It says if any particular case I assume automatically guarantees that the next case is true, then prove the first case is true, and then that automatically now means the second case is true. And the second one being true automatically means the third forevermore. That's why induction is so cool. We don't do this in general as proofs. We only pretty much do this on formulas because I have to have some pattern. Notice we don't do an infinite sum. That really wouldn't work, would it? Okay, let's do another similar one. Again, this is in Calc 1. we use the summation formulas when we're summing up the areas under the rectangles, and there's certain things we do right at the beginning, right before we integrate. What if I wanted to do the sum of I squareds? Ooh, that one's a little bit achy. That's n plus 1, 2n plus 1 over 6. Now, what I always like to do, we wanted to prove something was true the other day, and I love what a lot of you guys are doing. I don't need you to do this on your quizzes, but you actually plugged in a few numbers. That's what I would do. I wouldn't write it on the proof itself, but I plug in a few numbers. Right? We talked about this. I have to convince myself that I believe it's actually true. Because if I don't believe it's true, how am I going to prove it's true? Now, I could have easily written this formula down incorrectly. Because the only time I've ever used this formula in my life is in Calc 1 when I'm doing summation. I never actually use this for anything else. So let's just do a few. Let's just say we're going to add up the first 3. 1 squared plus 2 squared plus 3 squared. Well, what does this equal?
14.
That equals 14? Okay. On the other side, n was 3, so I have 3 times 4 times what? Times 7 over 6. Well, let's see, 12, is that also 14? Now, do I need to do, the sum of the first 10 or the 100 or first 1,000? No, I just want to make sure, okay, I think this formula is good. Okay, I think I wrote it down correctly. I kind of say that, with a wink. I think I wrote it correctly. Because I might have screwed up one of the coefficients or something. Okay, this is an actual summation formula. There's another one for I cubed. And in every calculus book we have these formulas, but this one you have never seen a proof for because the proof is actually quite complicated. But I can prove the formula is valid by induction. And let's do this. This one's a little more complicated. So again, what is the first instance of this formula? It would be n equal what? 1. Because I'm starting at 1, the smallest n could be is 1, and n can't be 0. So let's show true. I'm going to write down our goal. Show true for n equal 1. How do I do that? Well, let's see. The sum from I equal 1 to 1 of I squared is 1 squared. Okay, I know that. Now, let's plug a 1 into the formula. Oh, I'm going to put a question mark here. Does that equal 1 times 2 times 3 over 6? Yes? Good. I put a question mark. I'm saying, does it equal? And you're saying, yes, it does equal. Beautiful. Again, if that wasn't true, it probably means we have the formula incorrect. Is it possible when you're doing a problem out of the text that you write the formula incorrectly? Is that possible? Sure. Drop in a square, drop in a negative sign. We all know there's an infinite number of ways I can just simply miscopy something. If that wasn't true, don't keep going, right? Because there's nothing else that you can do. Second step, we will assume true for n equal k. So what I'm going to do is state the formula by replacing n with k. Think of k as a particular value, an arbitrarily chosen value, but a particular value. Okay? So now I'm saying this is the law. I equal 1 to k of I squared is equal to k plus 1, 2k plus 1 over 6. I'm going to assume that this is true. Whether it's true or not, I'm going to assume it's true. So now, what is the next term? So let's remind ourselves. What does this mean? This means 1 squared plus 2 squared plus 3 squared all the way up to n squared. That's what that means. So if I wrote the sum from I equal 1 to k plus 1, that would be 1 squared plus 2 squared plus k squared plus... Do you agree with that statement? Stare at that for a moment. Make sure you agree with that. Okay. Why am I writing it that way? Because we are assuming this part. We're assuming that. So what I want to do is write this down. What is the sum from I equal 1 to k plus 1 of I squared? Well, it's got to be the sum from I equal 1 to k of I squared plus the next term. Whether the formula is true or not, by the way, this statement is absolutely true. I'm not doing anything from the assumption. If I want the first k plus 1 terms, I wrote down the first k terms, and then I wrote down the k plus first term. This is kind of what we did before. Now I'm making the bold assumption of this equality right here. So now I can replace this with k plus 1, 2k plus 1 all over 6 plus k plus 1 squared. Y'all with me on that one? Now, I need to manipulate this formula. If I do everything correct, in the end, what do I want this to look like? Exactly this formula with n's replaced with k plus 1s. Y'all go on that? By the way, one of the things you love about induction is every problem's different, but you feel like you're doing the same kinds of steps over and over again. Because if I'm asked to prove it's true, why do I love being asked to prove it's true?
You know it's already true.
Then I know it's true. I know it has to work out in the end. You don't ever do a proof by induction to determine if it's true or to show that it's false. That's not a good use of this. And algebraically it would be a nightmare. I'm proving something is true, which means I know it's true. So it's got to work out in the end, and if it doesn't work out, it means because I messed up the algebra. It feels like cheating, but we're taking known formulas and now we're proving them. Formulas that somebody handed you. Have you ever been handed a formula in a science class? Yeah. Was it derived? Maybe. Maybe not. You know, chemistry, OChem, you have formulas? Probably not. Somebody did the hard work for us, and we're okay with that. When you guys leave today, is anybody here going to go quickly invent a combustion engine and invent some wheels and, you know? Probably not. You probably just got to get in your car. It's okay. You don't have to invent everything or prove everything you're using. But if it's a math situation, you want to be able to prove everything, even if you didn't. If you had Calc 1, if you remember Calc 1, if you had Calc 1 and you never derived any of your derivatives using limits, you just, here's the derivative formulas, memorize them, could you imagine there would be no understanding? That's business calc in a nutshell. In business calc, you're handed all the formulas. They avoid using the word limit. Limit is the equivalent of Voldemort in business calc. They don't do anything with limits. They just, here's the formula, here's how you use it, and you go, great. How do I know that it's true? How do I know how to get to the next thing? How do I justify an antiderivative if I don't have a limit or anything else? So rather than multiply all this out and then factor it again, I don't want to do that. Why? Why don't I want to multiply this one out? That'd be a cubic. This would be kind of an icky factorization. The previous problem, it was quadratic. I could live with that. So rather, why don't we be a little bit clever? I do want everything over a common denominator. So far, so good? How about I factor out the k plus 1 from the numerator? Okay, those of you who had linear algebra with me, right, when we were doing eigenvalue problems, remember? You usually had cubics, and I said, no, factor it before you get to the point of distributing. You rarely want to distribute this out. If we did a problem where the exponents were higher, I don't think anybody would want to distribute. It just gets too icky. It's not incorrect, but it's difficult to keep track of. So what if I wrote it like this? What's left? Well, if I pull out a k plus 1, then I have a k times 2k plus 1. Agreed? Then what else? Plus 6k plus 1. That's only going to be a quadratic. That one I can multiply out, and I should. So what will I get? I will get 2k squared plus k plus 6k would be plus 7k. Then what else? Plus 6. So far, so good? Can I factor that? Yeah, I'm pretty sure I can, because I know there are two integers that add to 7 and multiply to 12. And it's probably not going to be terribly challenging, so let me do this. Love our alias. I know that's going to be a k plus, and I know the next one is going to be a 2k plus. Agreed? So k plus what and what? So I got to multiply to 6. So is it 2 and 3? Is that what it's going to be?
Yeah.
Real
Yes.
quick check. 4, 7. Okay, good. Is this what I want? How about if I wrote this as k plus 1 plus 1? And how about if I wrote this as 2k plus 1 plus 1? Sorry, is that true? Stare at that for a moment. Is this correct, what I did? Why would I want to do that? Because it now looks exactly like this formula where I'm replacing n with k plus 1. So this would be k plus 1 plus 1, right? K plus 1, k plus 1 plus 1, 2 times k plus 1 plus 1. Is this a good thing? I am done. I really need to do this to make the formula look exactly right. You could also, at the beginning of the problem, say, if I replace n with k plus 1, what's the final form that I'm looking for? Some people do it that way. I kind of like that because that's even more obvious now. Okay, is this hard algebraically? Not really. Question?
So for the start of like step 3, why do we like split up the summation into like?
Well, because I don't know what this is, but I do know this. This is the sum of the first k plus 1 terms. I know that. Forget the formula for a moment. This is the sum of the first k plus 1 squares. Agreed? But what I'm assuming is the sum of the first k is exactly this. So I'm taking the sum of the first k, and then I'm adding this to it, because that's the next term. But I'm not assuming it's true for k plus 1. I am assuming that the first k give me this. And then I'm adding the next term. What if this formula, this is not going to happen. What if this formula actually wasn't correct? I simply wrote it down wrong. Would I ever be able to get this? Would that be possible to get this? No. So if the formula were incorrect, it is impossible to finish the problem and be successful. But the formula is correct, and we were able to finish. That's kind of goes hand in hand. Everybody cool with that? Let's do a product one. I love the summation ones because they're generally really simple to understand and interpret. And the idea with a summation, I'm always adding the next term. Okay? Let us do sorry. Thought I had it. Oh, here we go. Sorry, I was looking at the wrong place. I want to prove yikes. Now this one's kind of gnarly. All right. So what is my first case that I have to consider?
Base case.
What value of n am I going to start this problem with?
0.
0. The last two I started with a 1 because my summation started at 1, but this one starts at 0, so my first case. Again, I said a lot of the textbooks will actually say always start with 1. No, always start with the first case. Most of the time your first case is going to be a 1, but it's not always going to be a 1. I could start later on. You know, I might have this product start at 3, I don't know, arbitrarily, then that would be my first case. Now this one here is going to be a little bit more work. So what is it that I want to show, do you think, in the end? What do I want this to look like? I'm just going to, I'm gonna put this again, this is parenthetic, you don't need to put this. But at the end of the problem, how do I know when I'm done? I'm done when it looks like this. I'm just gonna restate this part. I'm done when it looks like what, do you think? Does that make sense? That's how I know I'm done, because my last statement that I have should look like this. If this is in fact true, I should be able to prove this. That's the whole point, the next term. Give me any positive integer, if I put it up there, you'd plug it in and say, yeah, I'm proving it's true, but you're not doing it one integer at a time, you're doing it for all positive integers. Okay, so, first step, I want to show true, what do we say, for what? N equal 0. If I start with n equal 1, it's not going to be true, but you got to be careful with that one. Start with n equals 0. So that means I equals 0 to 0 of 1 over 2I plus 1. Oh, I don't need parentheses there. Times 1 over 2I plus 2. Well, what will that be? I'm replacing I with 0. So this would be what? 1 times a half? Okay. Is that equal to 1 over 2 times 0 plus 2 factorial? It looks kind of complicated. Well, 2 times 0 plus 2 is just 2. 2 factorial is just 2. This so is 1/2. But is it equal? Yes. It was kind of complicated looking, but it is definitely equal. That's a good thing. Okay, if I replace I with 0, the left side and the right side are easy to verify. Too much writing here. All right. I'm going to assume it's true for n equal k, so I'm saying this is now the law. I am not questioning the validity of the next statement at all. Equals. Okay. But what do I know? What do I know? Well, I know that the k plus first term is not going to be added to this product. It's going to be multiplied. Oh, so it's going to look like the last problem, except it's going to be a times rather than a plus. Mr. Spam must have hung up quickly that night. Okay, so this is a lot of writing, I know. 2I plus 1, 2I plus 2. So that's a 1. 2I plus 1. I know it is equal to this multiplied by the k plus first term. Agreed? This is the product of the first k. What would the k plus first term be? So go over to here. That means I'm replacing I with k plus 1. I'll write it out the long way. Times 1 over, if I replace I with k plus 1, then what would the first term be? 1 over
2k plus 3.
Would it be 2k plus 3, everyone? And what would the next term be? If I replace I with k plus 1, then that would just be 2k plus 4. It is totally correct to write 1 over 2 times k plus 1 plus 1 and then simplify it. And it's just a lot of extra writing. I don't really want to write this whole thing twice. Is it okay to be lazy there? That's just simple arithmetic, but what if you make a mistake? Yeah, you can't make a mistake here. That'll mess you up. Now, I'm assuming that this is the law. This is an absolute truth. Therefore, what can I assume? That this is equal to 1 over 2k plus 2 factorial times 1 over 2k plus 3 times 1 over 2k plus 4. Again, this is our assumption, that these are equal. But the k plus first term is getting multiplied. Now, do you like the form of this? In terms of factorial, isn't this the next one and this the next one? So, for example, if I said, all right, I want you to take 6 factorial, I want you to multiply it by 7, and I want you to multiply it by 8. Wouldn't that just be 8 factorial then? So what is my denominator now? What is it? Won't it just be 2k plus 4? That's pretty simple to see, I hope. Is that a good result? Well, let me go one more step. True or false? 2 times the quantity k plus 1 plus 2, is that the same as this? Now, look at that answer. Is that exactly the result we would get here if I replace n with k plus 1? So is this a good thing? Yeah. Are we done? That may be the more important thing. Are we done? Yes. This is one of the big problems that a lot of people have with proof by induction. That's how I learned that. Check mark. I got exactly the original formula with n replaced with k plus 1. I didn't replace n with k plus 1. That was the result that I got at the end. Does that make sense? I didn't make it work. It fell into my lap here. Okay, kind of cool? All right, we'll do another one. Products, I went through a product, it's not harder. It's not by any means. In fact, some people might say it's easier because there's less factoring. But there's an unfamiliarity with this, all right? Most of us have never actually worked with this. We'll do one more of this type, and then we're going to move to a slightly different type of induction, kind of a higher level one. This is wonderful for simple formulas. All right, we're going to do one more. Let's see, which one are we going to do? Hold on. I saw it earlier, so let's find it again. Here it is. I want to prove that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus, at some point, 1 over n times n plus 1 is equal to n over n plus 1. Is it pretty obvious that that's what I'm doing? It's n times n plus 1, where n is starting where? So let me ask you, could you rewrite this statement as a summation? Yeah, that's easy. You know why? You have the general term right here. This one is just sort of thrown in to say, oh, sometimes I'm not given the formula in its formal state. I've got the formula in its expanded state. Isn't this the exact same thing as saying I equals 1 to n of what? 1 over I plus 1. Does everyone see it's the exact same thing? Because when I is 1, it's 1 times 2, then 2 times 3, and then when I is n, that's the last term. It is absolutely correct to write it as a summation, but it's actually not necessary. I can just leave it in that form up there. All right. So what is the first case? N equal what? N is equal to 1 because it's 1 times 2 and the general form is n times n plus 1. So that n's got to be a 1. It can't be a 0. I'd be in trouble if it were 0 because that would mean that's 0. And I don't think I'm going to get 0 as a result here. All right, so how do I do that? Well, that means that I'm only looking at the first term. I'm only looking at this term right here. Now, that equals a half. Does that equal 1 over 1 plus 1? So notice, my first term is 1 over the product of consecutive integers. I'm trying to show the result is the quotient of an integer over the next consecutive integer. I did not use that fact, right? Would you agree that that statement there looks very different than that statement there? So, but when n was 1, that first fraction equaled this fraction. If it helps you to convince yourself, if I take now 1/2 plus 1/6, 1/2 plus 1/6 is 2/3. Okay, think about it for a moment. 1/2 plus 1/6 is 2/3. So when n is 2, 2/3? I can do this all day, like Captain America, but I'll stop there, because otherwise, the fractions start getting icky because I have to worry about common denominators and all that. But we think we're doing it okay. So, assume true for n equals k. So what am I going to assume is true? I'm going to write it in this form. I'm going to assume then that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over k times k plus 1 is equal to k over k plus 1. I am going to make this assumption, that this is absolute. The best part about assumption when you're writing a proof, once you say assume something, that's the law. That is the only part that cannot be questioned. You don't have to prove your assumption. Your assumption should lead to a conclusion. Okay? So the ones that we just did last day, most people did a really good job, but a lot of times people forgot the assumption part. So you'd say, let's say for example, I wanna prove that if A divides B and B divides C, I'm gonna get some conclusion. So I gotta assume that A divides B. Some folks just start by saying, well, there is an integer out there such that A equals empty. Actually, that is an absolutely false statement if A didn't divide B. If A didn't divide B, then there exists no integer where A is a scalar multiple of that integer. Does that make sense? Oh, I have to make the assumption, or everything else I write is actually absolutely false 100% of the time. And I'm trying to write a proof that's always true. If I leave out my assumption, there is no truth. Everything is actually the extreme opposite. If, for example, I'm trying to prove my result is an even or an odd number, well, if I don't make the assumption my original number is even or odd, then the conclusion is actually absolutely false. But the proof was so simple. Yeah, but it was only true if you started with an even or an odd number, let's say. So if I don't make that assumption, then there is no next step. I'm making this assumption. This is absolute. Even if the formula is false, I'm assuming this is true. But if this wasn't true, then I will not be able to get my conclusion. My conclusion will be impossible to arrive at. Okay? So, third step, show true for n equal k plus 1. That's kind of messy. All right. So, if this is the sum of the first k, then I'm trying to show that 1 over 1, I'm just going to write the first 2. Okay, I know what this equals because I made the assumption. What is the sum of the first k plus 1 terms? Replace n with k plus 1. So that means I want 1 more. Okay. Do we all agree this is the sum of the first k plus 1 terms? Whether the right side is true or not, if I said what is the sum of the first k plus 1 terms, is that what it is? Yeah. But because I made the assumption on this, I can say this equals k over k plus 1 plus this. Okay? Now, my goal is to what? What is my ultimate goal? To get this formula where n is replaced with what? K plus 1. I can't just say it's true. I have to manipulate this and hope and pray that I get that result. Am I going to get that result? Yeah, because we're told that was true. But if I had made an algebraic mistake along the way, it's not going to work. All right, so what should I do now? Okay, I need a common denominator, so what am I going to do on the left side? Would that work if I do that? Yes, no, maybe? Yeah. All right, so now what have I got? I've got k squared plus 2k plus 1 over k plus 1 times k plus 2. Well, that doesn't exactly look like my finished form. Oh, wait a minute. Tell me about the numerator. Isn't that k plus 1 quantity squared? Can I cancel a k plus 1? What does that give me? K plus 1 over k plus 2. I'm good, but most folks and pretty much all textbooks would say go one more step. Why is this actually a good thing? It seems redundant, but why is this a good thing? Because now it looks exactly like the formula with n replaced with k plus 1, which is what you were trying to show. Pretty powerful stuff. If I take a formula, usually summations and product type formulas, and I want to prove it's true, induction is probably the easiest and cleanest way. Now, I want to take something that's a mathematical statement rather than an actual formula. Because I can also make mathematical statements and potentially prove them using induction. All right? Just 1 second. I want to prove sorry, I just want to make sure I'm not doing the quiz problem. I am notorious over the years. I'll be teaching a lecture, I'll just randomly make up problems off the top of my head, and I'll have people chuckling in the back because apparently the random problem I made up off the top of my head was exactly a quiz question that was due next week. So when I do that, have I ever done that for any of you? Yeah, many times. Well, you better not miss that one. That's all I gotta say. You better get that one right. I had a student complain one time, it was a calculus class. I inadvertently did exactly that. I had done the quiz problem, and he turned it in and got it wrong, and he wrote me a nasty email, said, "You did it in class, how could you partially mark it wrong?" I said, "I did it in class, and you didn't even turn in a correct, there was nothing correct." It's like, how do you miss a problem that I did in class? He missed every part of the problem, but he complained that he should have got 100% because I had done it in class. That's like saying, I said the answer is true, and then you turn in false. You know, yeah, it's probably not a good one. All right, let's do, I want to prove 7 to the n minus 1 is divisible by 6 for all non-negative integers. There's a whole bunch of these types of proofs. They're really cool. They're kind of fun. How many cases would I have if I want to do this in cases? Too many. All right, let's do it for n equals 0, 1, 2, 3, 4, 5, 6. But this is still the good idea part. You need to convince yourself that you believe it's true. I'm looking at 7 to a power, and I'm going to show it's divisible by 6. I don't know, that seems kind of iffy. All right, what if n is 0? Then what do I have? 0. 0 is divisible by every number. No number is divisible by 0. Don't get those confused. How do I know? Because 6 times 0 is 0. 0 is divisible by 6. Okay, let's put an n equal 1. 7 minus 1 is 6. Oh, okay. How about n is 2? 49 minus 1 is 48. Oh, n is 3. 343 minus 1 is 342. That's under 7. I think it's true. Is it true because it was true for a couple of cases? No, but I'm kind of convinced because I have to prove this is true, so it's probably true, but I need to believe it myself. If I used any number other than 1 there, do you think it would be true? Yeah, it's probably not true in general if I just randomly took a second number. So that, So this one here is going to be a little bit trickier. All right. I am writing the instruction. When you're writing the proof, you do not necessarily have to write the line I'm writing to show you, hey, this is what we got to do first. This is what we got to do second. This is what we got to conclude. A lot of folks will write a clean proof without saying this, but what do I have to show it's true for?
0.
0.
Base case.
I gotta show it's true for all non-negative numbers, so my first case has to be at the 0. Okay, and I'm writing that down to make sure that I'm doing it correctly. By the way, if I accidentally start with a 1 or a 2 or a 3, it's still gonna work, isn't it? But I do need to find out what is the first case that's true. Because what if I, just for hypothetically, just for the heck of it, what if I started and I showed it was true for 2, and I made that my first case? And then I finished the proof successfully. Then you know what I proved? It's true for all n greater than or equal to 2. Oh, but that I want it to be greater than or equal to 0. That's why I have to start with 0. Then when I do the induction part, if I'm showing, assuming it's true for any case, then the following case must automatically be true. Then if I proved it's true for 0, that means that 1 is automatically true. And then it means that 2 is automatically true. That's how induction works. So it's always a counter, okay? I'm not proving it's, generally speaking, I'm not proving it for real numbers. Why? Because I need a k and a k plus 1. I need them to be integer. That's why this is limited. You can't do this for everything. But when it works, it's so much easier than other proofs. So if n is 0, I think we just did that, then 7 to the 0 minus 1 equals 0, and 6 divides 0. Let's keep it. That is a true statement. Because 6 times 0 equals 0. Then what we're going to say is, I'll write it like this. 6 divides 7 to the k minus 1. Okay? Everybody good with that? I'm sure I wrote that one down correctly. Now, third. So, any suggestions? See, I'm going to have, right, the next thing I'm going to have is 7 to the k plus 1 minus 1. And I need it to equal something. But it's not like the last case where I'm just going to add the next term. I'm just going to multiply the next term. Ew.
7 times.
Let's go back to this step. I have to manipulate this at some point. And I'm assuming the 6 divides by this. But in every other case, my assumption was an equality, wasn't it? Didn't I assume something was true? I don't have an equality. I assumed a mathematical statement. Okay, so what does that mean? How about there exists t in the set of integers such that what?
16 7k.
All right, 7k minus 1 equals 6t. Okay. Is this a start? How can I use this now? Oh. So what does this equal then?
7k.
Is that true mathematically?
Yes.
Everybody okay with that?
7k minus 1 and then substitute in
So
16.
I have 7 times 7k, and then I'm subtracting 1 from that. True? I can't substitute here. It's not 7 times the, by the way, be very careful, it's not 7 times the quantity, it's 7 times 7, then I'm subtracting 1. Do you see where we could easily make that mistake? Oops. No. So I'm just going to here. Oh, let me replace 7 to the k with what? 6t plus 1. If this is true, then this is the law up there. That cannot be questioned. Now I'm just saying, what is this quantity? This quantity is this, and now using my assumption, it's this. If we do it right, induction proofs tend to just roll off the tongue, right? They flow beautifully. I really love these kind of things because there's some really complicated problems that we can do. The bonus question I asked you for today's quiz is really challenging. But because I'm asking you to prove it's true, then you know it's going to be true, so it has to work at some point. What do I got now? 42t plus 7 minus 1, which is 42t plus 6. Well, how does that help me? Well, actually, that's a good thing, isn't it? Can I write this as 6 times 7t plus 1? Tell me about 7t plus 1.
It's an integer.
It's an integer. Oh, again, this is one of these things, a lot of us when we're writing proofs, we forget this, but this is actually critical. 2 things. That's an integer, which makes, I cannot say anything about divisibility unless I have integer multipliers. This is an integer since what? Addition and multiplication. You guys know the, we should come up with like a code word, you know. Asterisk is, you know, when you do something enough times, you know, by asterisk. Okay, addition and multiplication of integers is closed. Okay. Okay, so why don't you want to rename this? Yeah, I probably should have done that first. What letter? How about S? Okay, S equals 7t plus 1 on that one, and that's an element of the integer. I'll write it like that. That's probably a little cleaner. So what does this now mean? That this is equal to 6s. I've got 7 to the k plus 1 minus 1 equals 6s. Doesn't that imply that 6 divides 7 to the k plus 1 minus 1? Again, the key is I wrote it as 6 times an integer, and I proved this was an integer. It's very important that we actually, at some point, make the statement s is actually an integer. Sometimes we forget that. Okay? Kind of cool, wasn't it? We didn't do this for a sum of terms. We didn't do this for a product of terms. We did this for an individual term that's just out there floating around in space. I said, well, 7 to the k minus 1 is always divisible by 6. Now, that seems like a stretch. I have to prove that for all values of n? Yikes. Well, okay, let me convince myself it's true. So we plug in the first few, right, small integers, and okay, yeah, it seems to work, but that does not constitute a proof, right? So the assumption that it's true at some point leading to the next one, this didn't really involve cleverness. This involves stuff we've been doing already, didn't it? Everybody good with that? Okay, any questions so far? Like I said, deduction proofs are kind of fun. They roll really well. Now let's do one more, not an equals. We're going to do an inequality. Well, let me find it. Okay, hold on. Find which one I'm going to do here. Okay, here we go. This is actually one that some people use it as a formula. I'll do it over here. Sorry, and it is. Now, by the way, this is something, I don't know if you remember sequences and series, but I wanted to use something like the direct comparison test. We love direct comparison because it's the easiest algebraically. But a lot of times in the direct comparison test, I was comparing two sums where, wait a minute, I'm trying to show that this sum is smaller than this sum, but its first few terms, it's bigger. It might have taken 3, 4, 5, 6, 7 terms, and then it's smaller forevermore. So I would say this term is smaller than this term for all n's greater than some number. You guys remember doing things like that? We didn't say it was always true. It was always true at some point. Stare at that for a minute. Is this statement true? I want to prove this is true. Well, if n is 0, it's 1 is less than 1. Okay. If n is 1, then it's 3 is less than 2. Oh. If n is 2, then it's 5 is less than 4. This ain't working. If n is 3, then it's 7 is less than 8. And the right side's exponential, which we already know is going to grow significantly faster than the left side, which is linear. Is this statement always true? When is it true?
Well, greater than or equal to 3.
This is important, and again, if we knew this kind of concept in general, back when we were doing Calc 2, a lot of the times when we did things, it would have made more sense. Because some of the comparison tests, it didn't have to always be true, it had to be true for some point on. Do you guys remember doing things where you were looking at summations and the terms got infinitesimally small? And then later got really big. I'll give you a simple example of one you did in Calc 2. I'm considering something like this. You know, something ridiculous. Now, if I start plugging in values of n, I mean, these numbers are like to the sun and back kind of big. Do you agree? You know, this is absurd. But your numerator is an exponential and your denominator is a factorial. So there will be a point when this is when the denominator actually catches up. It's going to be way down the road. These are going to balloon beyond reckoning. The numbers are going to be so big. But there's going to be a point, I don't know where it is, maybe it's 1,000, maybe it's 1,000,000, maybe it's 1,000,000,000, where this is going to dwarf this, and these terms are actually going to go to 0. Isn't that crazy? But what we always make the mistake of in calculus is we only look at the first few terms, and we're talking about limits to infinity. You don't look at the first few terms to figure out where it's going, you look that way, way, way down the road. Agreed? So if I'm trying to show that that term, let's say, is going to 0, or the sum of those would actually be finite and converge, it might converge to an absurdly large number, but it actually will converge because the terms are going to go to 0 eventually because of the factorials. So I love doing problems of that nature, just, you know, kind of defies everything. So, well, in this case here, that's exponential. That has to dwarf. If I graph these, but maybe that's the thing. Maybe if I start by graphing it, maybe it's more obvious. This is not part of this course. This is more of a common sense thing. What does 2 to the n look like? Well, it's this. Okay? Am I interested in the left of the y-axis in this case? No, because I'm not interested in negative values of n. And the other one's 2n plus 1. Okay? So when n is 0, I am at 1. And it's not a great graph. Can you all see it though? There's a place where they cross. 2n plus 1 will equal 2 to the n, but it won't be a rational number. I'd actually need to use Newton's method. Okay? How do I know? Because when n is 2, this is bigger than this, and when n is 3, this is smaller than this, so somewhere between 2 and 3. Agreed? So does it make sense to you to go, okay, I believe that statement is true. I'm doing it a completely different way. I believe the statement is true because I think about it graphically. Yeah, 1 is going to go much faster. So I first had to convince myself that I believe it's true. Now, how do I prove it's true? Well, let's start with our first little guy. See, the question I would ask you is this true? And you'd say, well, no, it's not always true, but it is true from this point on. I think we'd all agree. First of all, it's true from this point on. Now, prove it. Well, would the graph do it? Would the graph or a graphical representation, if I brought it up, would that be a convincing evidence for most people? Yeah. But I want to prove it numerically. So, case 1, show true for n equals 3. Okay? So 2 times 3 plus 1 equals 7, and that is smaller than 2 to the 3rd, which is 8. Okay? It's an inequality this time. So we will assume it's true for n equal k. So the assumption that I'm going to make is that 2k plus 1 is smaller than... Now, here's something that we didn't really talk about. I'm making this assumption for k. Is this for all real numbers, k? It's only true for k. Why? Because my domain in the problem is only numbers greater than or equal to, integers greater than or equal to 3. By the way, in this case, does n actually have to be an integer for this to be true? No, the way I wrote this problem, in the previous problems, when we were doing factorials, or we're doing divisibility, these have to be integers. These have to be integers because we're doing divisibility. Divisibility doesn't apply when we're doing fractions. So the nature of the problem, I didn't have a choice. Does that n have to be an integer? No, but when I'm doing the induction proof, I'm going to use +1. I'm going to use integers. So for these problems, generally it's assumed that you're doing them for integers. But it turns out this is true. But is the first instance of truth the number 3?
No.
Remember, I just said somewhere between 2 and 3, it's an irrational number. Oh, okay. So when you were doing problems in calculus, and you said, okay, it's not true for a while, so I'd say, well, do you know when it's true? Yeah, somewhere maybe between 5 and 10 it's true. I said, okay, then just say from 100 on. Just pick an arbitrarily large number. Then I know it's true from that point on. Does that affect the truth of my conclusion? Not at all. It wouldn't matter if you started later. It wouldn't affect the truth of your conclusion. But we're going to do it only using integers because we're starting with an integer value and then going from there. That's kind of how you know the difference. I could do this for all real numbers, but we want to do it just for integers. So we're assuming that one. So now let's go to the next case. Now this is kind of tricky. I'm now going to replace k with k plus 1. So we've got to be a little bit careful. So what am I going to do? If I replace k with k plus 1, then what am I actually adding to the left side? 2. So let me write it like this. If 2k plus 1 is less than 2 to the k, does that imply that 2k plus 1 plus 2 is less than 2 to the k plus 2? I'm being sneaky and clever right now. Is that true? If this, then I just added 2 to both sides. Why would I do that? Because now what is the left side? It's 2k plus 1 plus 1. And I'm saying in absolute certainty it is equal to this. Can you factor a 2 out of this? Can I do anything with that? Do I want to factor a 2 out of that? How do I manipulate this?
2k minus 1. Let's do, and then you can take 2 out.
Yeah, kind of work myself into a corner here. I don't have a whole lot of room to write. But what I want to get is the 2, I want to get the k plus 1 at some point, okay? Now here's the thing. You said this is that. What I'd really rather do, where are we? 2, is this, oh, sorry. Let me write. I don't have room to write this. I apologize. I left myself in kind of a bind. We all know this is true. Okay, let me leave it like that. We all know that's true. Our mistake is to try to use equals. Our mistake is to try to use equals. Is this smaller than 2 times 2 to the k? Remember, k is greater than or equal to 3. Is that a true statement mathematically? And what's this? When I said, can we factor it, that is an absolutely true statement. But what would be the problem with factoring it? I think you said it correctly, Casey. What's the problem with factoring? I wouldn't get a k plus 1 as my exponent. I'd get a k minus 1, which means I'm going in the wrong direction because I'm trying to do equals, but this is an inequality. All I got to do is maintain the inequality. Now, are we done? Yeah. I just proved this statement replacing k with, or n with k plus 1. And it was the cleverness of doing this. Adding 2 to a quantity is not as much as multiplying the quantity by 2 if the quantity is already greater than 1. Everybody get that? That was why we went through the first few cases. That one there is a little trickier. But what makes it kind of nice is that, again, I know it's going to be true, but I just have to make it look like the form. All the other problems, they were equals, so it was easy. This wasn't that case.
So it seems like, to me, what you just said, so adding 2 to quantity is less than if you multiply by 2.
If
That
the
seems
quantity
like-
is past a certain point.
That seems like something I'd have to do another whole proof. Or
No,
would I
because
just, like,
remember, we're starting with n is 3, so we've already looked at the numerical values. We started at n equal 3. So if we started at n equal 3, then I know 2 to the k is at the very smallest 8. That's the smallest 2 to the k is. So the smallest this could be in this problem is 8 plus 2. The smallest this could be is 16. Does that help?
Yeah.
Because that's why at the beginning, the not starting until 3. What if I was actually starting at 0 or 1? Then that statement would not be true for all values starting there. That's what once we have our starting point, inequalities are a little trickier. All right, I'm going to stop there. Now what I want to do is do the review. I want to talk about the test, because the one thing about exams, everybody has to be prepared. Everybody needs to know what's on there. Let me erase some of this. I'm going to bring up the practice test. Now, you all know you actually have 2 practice tests. One is a sneaky practice test. What's the other practice test called? The quizzes, yes. You have 2 sets of practice tests because, as I always tell people, I don't care if you got 100% on a quiz. I don't care if you got 0 on a quiz. What do you know the day of the test? If you got 100%, and all of you who are in calculus, you understand this. First quiz for the next exam, you got 100%, but the exam might be 5 weeks later. And you might not have done a similar problem in the meantime. Is there any guarantee you're going to remember how to do that the day of the exam if you haven't done a similar problem? Maybe not. Now, this course is going too fast for you to forget things in mass, but it's also going so fast that it's hard sometimes to categorize and separate things. And that's one of the things you have to be able to do. Here we go. Bring this up. And the other thing I always tell people, I don't care if you miss a problem completely as long as you figured it out. Because on the exam, you're doing the quiz problems, but they have much greater weight. So mistakes on quizzes are absolutely forgivable. No one should ever get bent when they make a quiz error. But it's repeating the error that's the problem. You gotta fix it, okay. A lot of the problems that you're going to be asked to do will look really of a trivial nature. Okay, this first thing here, would you agree this is not a complicated question? Okay, today is Thursday the what? The 15th. I'm going to ask you this question on Thursday, June 1st. Do you have any chance of answering it correctly? Probably not. You have no idea what I'm asking. You've never seen that language before. What does that even mean? Cartesian product. In other words, you couldn't have answered this question before you came to this class. But you came to this class, you say this is an easy question. Easy is relative, isn't it? Asking you this question. Now, if I gave you a 2x2 matrix and asked you to find the eigenvalues, it's trivial if I've had linear algebra. If you haven't had linear algebra, you could spend a month researching the question, wouldn't have any idea what I asked. Easy is relative. If you know how to do the problem, yeah, most of the problems are going to be easy. But these are problems you did not know 2 weeks ago. So that's why you got to kind of put it in perspective. So I'm going to ask you something like this. This is not meant to stump you. This is really, do you understand the definitions of what I'm asking you? So the first thing is getting the Cartesian product correct. This is probably a little bigger than something I might ask just because I don't want people to get lost. But how many how many elements are there in my Cartesian product before I start? Do you know? 15. Because I'm matching 5 with 3. That's a statistic thing. It's called the matching property. If you have K1 ways of doing the first thing and K2 ways of doing the second thing and K3 ways and so on, how many ways can you do the whole thing? You multiply the possibilities. There's 15. The reason I'm mentioning that is, believe it or not, when I asked this question on the quiz, a couple of folks didn't get all of them. I think we had 4 and 2. So there should have been 8 elements, but there were a few answers that only had 6 or 7. That's kind of careless, I know, but that's a quick check. Okay? Now, is whatever my t is going to be, it's probably not going to be a function. Why? whatever I define T as is probably not going to be a function because I'm reusing elements from the domain. Reusing elements of the codomain did not affect function. What does that affect? Something totally different. No. Reusing elements, think like a parabola. I'm reusing elements of the codomain.
Oh, the symmetry?
A parabola is still a function, but it is not one-to-one. Reusing elements of the domain means it's not a function. Reusing elements of the codomain means it's not one-to-one. They're completely different animals. Another way of thinking of it, if it's not one-to-one, then its inverse is not a function. We're going to talk about that kind of stuff much, much later. Okay? That's not the part I care about. It's the part that follows. Whenever it's y, is the statement valid or invalid? Why is it invalid? Oh, why is it not a function? Yeah, of course it's not a function. That's easy. Something about just simply I'm reusing elements of the domain. Some of you are going, well, it doesn't pass the vertical line test. Well, there's no graph, so that's kind of a silly one. You actually have to have a graph, and no, don't graph. That's just silly. Now, the really important types of questions, right? Biff loves wings. Biff loves ping pong. Biff loves the color blue. Biff is simple, okay? So now when we write this, parentheses are important. Why are parentheses important? Because sometimes there's a distributing going on here. Now, I gave you two versions. Which is probably an easier one to work with? The first or the second?
The first one.
Probably the first one, because could I do this, the one on the left, could I technically write that without parentheses?
Yes.
Yes. That literally is the associative property. When you're doing the same comparison, if it's all ors or all ands, you actually don't need parentheses. If you have ors and ands, you have to have parentheses because of the distributive property. It will be a different interpretation. Now, why did I show you the second one? Well, because when I make my truth table, if I was doing this as a truth table, this one here, if I was doing my truth table, the second one would actually be a shorter truth table, because I wouldn't need the negations of W or the negation of P. In the first one, I would need the negation of W as one column, the negation of P as one column, and then that and as one column. Agreed? But if I did the second way, all I need is the or, and then the second column would be the negation of the or. It's less stuff. So that's what I'm showing you. Both of them are absolutely the same. Now, use a truth table. Right now, this is not an area of challenge for anybody. You guys are really good. But because we've used truth tables where we're looking at columns and truth tables where we're looking at rows, this is where we get into trouble. And you notice I made them bold. What most of us do, and here's what I'm not going to do it, but most of us put a little up arrow here and an up arrow here and saying, I am looking at these two columns to make my conclusion. What if, there's no reason for this, but what if you put, I don't know, sometimes you guys will actually put this guy before these guys, like you can't get this guy without those guys, but you might put them out of order. You know, some goofy reason you put this somewhere else. Does that make it wrong? No, it just makes it a little bit harder to see. I like the arrow underneath because you're saying, here is how I'm making my conclusion. A common error, and this has happened more than once, is people are saying it's false because these are not all truths. No, it's not a tautology because they're not all truths. No, I'm asking you, are these statements logically equivalent? That means, can I put the 3 bars between that and that? What's your conclusion? Yes or no? Yes, because their truth values are exactly the same. They're logically equivalent. Logically equivalent doesn't mean they're absolutely always true in all cases. No, that's what a tautology is. I'm just saying the left side and the right side are identical statements. We're actually proving the distributive property here, by the way. So don't say it's true because of the distributive property. No, you're proving it's true with the truth table. The nice thing is, in this case, if you had insight to what we've done before, you suspected that it was true. What if I changed one of these symbols? Maybe put a negation in front of it, or just change one thing. It's not going to be true. But I'd still have to do the whole problem, and then I'd look at the last columns and say, no, they're not identical. I want to point that out because it's possible I can have something that's not true. Some of the questions in the text is, determine if this is true. I know you hate that. But if I said determine if this is true, would there be any more work? No, I did the exact same thing and I compared the last two columns, but I'm comparing columns. Okay, that's really important. Okay. All right. Necessary and sufficient conditions. A lot of you are taking your necessary and writing it in a positive sense, which is not incorrect, but it kind of misses the point. A necessary condition is, if A is necessary for B, then not B implies not A is how you actually determine it. So you could say not A implies not B is also true, but that's what the necessary generally means. If I don't satisfy it, then the conclusion is not true, right? So if you are not a hockey fan, then you are not royalty. How else could I say that?
If you're royalty, then you're a hockey fan.
If you're a royalty, then you're a hockey fan.
You would accept both of them?
Yeah, they are equivalent statements. But from a necessary condition, a necessary condition for royalty is being a hockey fan. But does being a hockey fan mean you're going to be royalty? No, it means not being a hockey fan means you're not going to be royalty. That's why I'm saying think of it in terms of necessary. Sufficient for most of us is easier. A sufficient condition to get an A is to get at least 90%. I got 90%, I got an A. Now, does that mean if you didn't get 90%, you wouldn't get an A? No, it means if you didn't get an A, you didn't get 90%. So that's why sufficient conditions generally are positive in that way. Okay? A sufficient condition for knighthood, this is true, I actually looked it up. A sufficient condition for knighthood is to get an A in this class. Okay? So if you get an A, you can be a knight.
You will be.
You will become a knight. I don't think you have a choice. I think though, I was looking at, I think it means you have to move to Las Vegas and take up hockey. I think that's the version, All right, okay, let's keep going. Is this different from the previous truth table in how I'm asking the question? No, what did I say before? Determine if these statements are equivalent. Now I'm saying determine if this is true. That's exactly the same question. I always love doing this. Every class I teach, most of you have been there, I will use different words or different notations sometimes for the same question because there's a lot of ways to ask the same question. Simplest analogy I can give you, you're in Calc 1. You're in Calc 1. So I want the derivative. How do you know which one to use? Well, was your function defined y equals or was it defined f of x equals? That determines the derivative. So what do? I do each problem equally so that you get used to notation. So a second derivative, I can use this notation or I can use this. What you don't do, you don't use f prime if your function was a y. You don't use dy dx if your function was f of x. You use that notation, but we've seen different notations. Differential equations, it's even worse, right? We throw in the big D. And so if there's more than one way of saying the same thing, I try to use every way at some point so that you go, oh, that means the same thing as this. Just same question exactly, except I'm giving a symbol rather than words. I'm asking, are these statements logically equivalent? You do the problem. That's supposed to be clean. That really is supposed to be clean. So your conclusion is yes, because your truth tables are identical. And again, same thing here. Now, in this case, hold on. Where are we? In this case, what I did was I used the algebra. Now, question always comes up on every exam. One of the most important questions is, not what's on the exam, is what can I bring? Will you need a calculator? I don't know, probably not. Bring one anyway. What you're going to need is the logical equivalences on 2.1. Okay? What I mean, what are the logical equivalences? I have a fourth edition here, sorry. In the fourth edition, it's page 35. That's not the same as in the fifth, because in the fifth has an extra section. But it's the big blue. These are the reasons. If I said, where are we? Look at number 9. What am I doing in number 9? I'm using logical equivalences. I didn't say what they were, but if I said, okay, support each step, what is the reason that you can do that? Okay? Notice what I've got here. What did I do? I used the distributive property. So I have P and not P. I'm sorry, P or not P and Q or not Q or not Q. Well,
So I actually did this question using truth tables. I assume when you give us something this big, you probably shouldn't use the truth table, right?
probably using, technically we'll call it algebra. You want to do this one using algebra.
Yeah.
By the way, if you use the truth table and got the right conclusion, did you do it correctly?
Yeah.
Yeah, but you probably used a couple sheets of paper, right?
It was a thick piece of text. I won't lie.
What's that?
It was a very thick piece of text.
Yeah, I did not tell you how you had to do this problem. I would, in this case, determine their equivalent. You're going, you know, I have distributive properties, I have stuff going on here, and I have things like P or not P, right? Or Q or not, P or not P is always true. That's a tautology. That's, in other words, that's why I would want to do it this way. Okay, now, this is the one, again, we sometimes get in trouble. I'm using a truth table, but my answer is not coming from columns. Now it's coming from rows. And I would strongly encourage you, no matter how you do it, is the therefore not are, you gotta make not are the last column. Do you have to? No, you could have started PQ not R. Okay, I have it at the beginning, because I needed it. But if I don't make it the last column, when I'm trying to determine the validity of this statement, I'm looking at things and then I'm looking backwards, and there was more than one person who had a perfect truth table but an incorrect conclusion. Because they didn't, in this type of problem, they had left their negative R over here. And the T's, do you see how it's kind of confusing now to figure out, okay, which is the correct assumption and the conclusion? Because my conclusion is not the last thing. Just a general rule of thumb, always make your conclusion the last column, even if it means you repeat a column. Then there's no way you can misinterpret. So how do I determine my answer? There were 3 conditions given. And if I do this wisely, those 3 conditions are the last 3 columns before my conclusion. You got it? I really want to do them in that order because it makes my life easier. Okay? So now, all right. True, 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 everywhere where the 3 premises are true. How many places does that happen? 1, 2, 3. First 4 rows, that's true.
Not the first one.
Yeah, that was the top one.
Oh, I'm sorry. I can't see my fat. Sorry, second, third, and fourth rows. They all look fat. The second, third, and fourth rows, my premises are all true, but in this case, my conclusion was false. I want this to be an easy decision because I have it right there and everything's in the right place. You could all do this differently and get the right conclusion, but if I don't do it in that order, you all agree that determining my conclusion correctly is a little more iffy because my eyes are having to move around the table and find things. And what I found in general, that when people did it in the correct order, nobody made an incorrect conclusion. When people did it out of order, there were several, not all, but several incorrect conclusions because we just read it wrong. We made it harder than it had to be. So this is the type where I'm looking at rows. It's a therefore, whereas the other one I'm doing logical equivalences. I am not saying the first 3 things are logically equivalent to the last thing. No. I'm saying the last thing is a logical conclusion of the first 3. Okay. Everybody okay with that? And truth tables in general, everything but the final conclusion, people are getting right. But it's how do I make my conclusion?
So all the premises have to be true for you
To even consider it.
that
though.
you would look
Yeah, let's go back. So you're looking at the last column, oh, I see a whole bunch of falses. Yeah, but like right here, see that? The 3 premises were not all true. So it doesn't matter that that one's false. Remember, if I say if A then B and A didn't happen, it doesn't matter what happens with B. I didn't lie to you. A happened and B didn't happen. I lied to you. So the premises all have to be true in order to determine is that a right conclusion. Because if any of the premises are not true, it doesn't matter what the conclusion is because, you know, the first part wasn't fulfilled. All right? Most of us are pretty good now on the translations. One of the things about this class that you really want to be strong is taking words to symbols, symbols back to words. And we've done a lot of practice, and again, as a group, we're really strong on that. That's not really an issue. Which is the hardest one for all of us? Always, whether it's words or symbols, it's always the negations. The negations are the ones that tend to give us more trouble. So just be mindful, you know, when you're doing a negation of a statement. The negation of a for all, let me do it in simple words. The negation of a for all is,
There exists.
is there's at least one not. The negation of a for all not, at least one
True.
is. The negation of there is at least one,
For all not.
for all not. You can't say not, it's always not, because that sometimes, how do I say that logically? So for all not. Not, it's never true, that's correct. So for all, it's not. There's at least one not. The negation of that is?
For all, yes.
For all it is. The negation of a for all is that there exists. The negation of a there exists must be a for all, but in the other direction. Everybody okay with that? If the negation of a for all was another for all, then we're saying that then the negation of the full is the empty. No, it's just the not full. We have to remember that. The negation of empty is not empty. Isn't full. Is full included in not empty? Yes. So it's half full and a quarter full. Okay. Okay. Sometimes I'll say use quantifiers. Sometimes I'll say don't use quantifiers. The words for all and the words there exist are the same as the symbols. They're still quantifiers. So if I wrote for all and I say this without quantifiers, translating the for all and the x as ex and r as the no. Just say in words every. There is one. There is but it's just I'm trying to avoid. You're talking to your friend or you're texting your friend. Nobody speaks for all and there exists. In other words, use simple language. Make it easier on yourself. Sometimes I'm laughing when I'm looking at the language that we're using. It might be correct, but nobody speaks that way. Okay. Again, most of these are areas of strength. Conditionals. I will ask a question, kind of like the Luke, I'm your father. Or what was the other one we did? Didn't we do it too?
Lannister.
No.
On the notes we did.
Okay, did I put one on here? I don't even know if I did. Okay, we had a quiz, the Luke, I'm your father, join the dark side, okay? I cannot give you the converse or the contrapositive or the inverse of the negation unless I first have the conditional. So if you concentrate on getting the conditional, the other ones are automatic. Everybody realize that? If I make a statement and you can put it in if-then form, if P then Q, then all four are automatic. The rest of them are all automatic. The converse is if Q then P, the inverse is if not P then not Q, the contrapositive is if not Q then not P, and the negation is not an if-then. What's the negation of if P then Q? P and not or. By the way, it's okay to say but. Some of you say but. If you're speaking, I went to the store today, but I forgot to get the milk. I went to the store today and I forgot to get the milk. Is that exactly the same statement? Yeah. I don't care if you use but instead of and. If the sentence makes more sense to you, like this is how I would talk, then use but. But and but in that context mean exactly the same thing. But remember, the negation of a conditional statement, an if-then statement, is not another if-then statement, and sometimes that's where we get in trouble. When do I use a there exists? I'm sorry. When do I use a such that? I just gave it away. Only with a there exists. There exists something such that something. For all this, that. No, that's how we always say it. For all this, comma, that. There exists a this such that, that. Okay, being really formal here. And so sometimes we get them kind of misplaced. It has to kind of make sense. Okay, I love this one, the reorder. I did not ask this on a quiz. I usually, sometimes I do, sometimes I don't. You can absolutely order these in a way that it makes sense. But I also might have negations. What if I said one of these in a negative sense? You might have to rearrange it in your head. So for example, let's take all dogs are happy. What if it said no dogs are unhappy? If I said no dogs are unhappy, is that the same as saying all dogs are happy? Yeah, but the statement might be, it might be a negative statement and you say, oh, I need to translate it because of these. This is a really good question of This is called, if A then B, if B then C, if C then D, then A then D, that's called what? Transitivity. It's transitivity of implications in this case. So you're saying, okay, if this leads to that and that leads to that, so of course, the conclusion, all dogs go to heaven, we all know that. But like, happy creatures love and consume IPA, that's part of the process. It's kind of like the 6 degrees of separation, right? All right, more translating. Now, I'm going to ask you several proofs. We've done several types of proofs already. I'm asking you one of each. But I'm also giving you the option, I'm giving you more than you have to do. I always do this on tests if I can. We have 2 hours. No one here is going to need 2 hours. So I think I've given you, I've given you 6 proofs and you have to do 3, I think is what I got. So one of them might be an odd even, one of them might be a rational number, one of them might be a divisibility, one might be, use a, not a counterexample, I'm sorry, use a contraposition or a contradiction. In general, never start a problem saying, I'm going to try to use contradiction or contrapositive today. The problems we did today, could you imagine trying to do those by assuming not? The algebra would be mindless. You go, I don't even know where I'm going. No, these are all direct forward. If I'm trying to show something is not true, either always or not true once, that's when I'd say, okay, let me assume that it's true and show that it leads to a contradiction. That's when you would use that type of proof particularly. Okay? Or I simply in the instructions say use a contradiction or a contrapositive. So the sum of 2 rational numbers is rational. I don't want any negations here. This is too easy to go straight forward. So if you can do it straightforward, you never want to go the other way, negation. That just makes it harder. But the pieces of the puzzle, we know this is true, so it should be easy. I first have to create, I think, what am I assuming? I'm assuming R and S are rational numbers and that they are quotients of integers. I got to start with something. Then somewhere in there, I'm going to use the closure of addition and multiplication of integers, and it's a fairly simple thing. Now this one here, I'm saying, is it true? Ooh. So I'm saying, is it true? Don't assume it's true. Don't assume it's not true. Just go forward. And either it's going to work or it's not. So if n is 3k plus 3, then n squared minus 9. Well, what is n squared minus 9? Oh, it's 9 times k squared plus 2k. That's clearly divisible by 9. I know all the pieces of the puzzle. So let's change one thing. Everybody in this problem change one thing. What do you want to change?
N squared minus 8.
Okay, I like it. Let's make it n squared minus 8. What's going to happen in the last step? When you by the way, you're going to factor out the 9 because you're looking for divisibility. But what are you going to have in the last step? The evil F word. Fractions. Do you all agree you're going to have fractions in the last one? Which means that will not be an integer. So if it works for n squared minus 9, it's pretty much obviously not going to work. Unless I'm adding multiples of 9 to that answer. Does that make sense? So you can say, if I said determine if it's true and we made it n squared minus 7, you're going to hit a brick wall, run into it, and said this is not divisible. But you're still probably going to go forward. Now, show show 9 does not divide n squared minus 7. So you might say, okay, let's assume there's at least one n where it does, and then you can show the contradiction. We did a problem like that. In fact, you turned in a quiz problem like that. Now, divisibility ones, they're usually kind of nice. This is one of those rare times where I said, this makes perfect sense. A divides the sum, therefore it divides them individually. Oof. 4 divides the sum of 3 and 5, correct? But 4 does not divide 3 and 4 does not divide. Oh. So this is one of those rare times for the quiz, or excuse me, for the practice test, I actually gave you one where you could easily find a counterexample. Hopefully you didn't try to prove that was true. You said, no, that's not going to work. Not that time. Okay. Everybody okay with that? All right. And now this is the one that gives us trouble. Show that for any integer, this is not divisible by 4. So how do I take every single integer and show that they all keep failing over and over and over again? That's hard to do, isn't it? Okay, now in this case, why odd and even? Why would we go odd and even?
That covers all integers.
Well, because it's actually true for the odds. It's not true for the evens. Oh. So if I'm trying to show that this is always false, is it always false?
No.
No, it's always false for the evens. It's always true for the odds. This one's way trickier. This is probably the hardest type of question. I am not going to ask you a cases problem. I'm going to ask you this question. Actually, you know what? I think I changed the question on the practice test. Oh, I think I changed the question on the practice test to even. I just didn't change the key. I thought I did. Question? Yeah.
Why can't you just disprove it by counterexample?
Well, because of the. I'm trying to show for any integer, and it's infinitely true, but it's also infinitely false. It's a odd and even.
But if we have for any integer n, that is not divisible by 4. If I provide an integer n where it is, aren't I done? Because if n is 3.
Well, that's the question. When is it not true? When is it ever true or is it ever not true? In this case, again, it's an odd and even thing. The way I'm going to ask this question is, show that for any even integer, or show that for any odd integer. I'm actually going to change it so you don't have to do cases. Then okay, because odd and even always have cases. We did a problem a little bit earlier where it wasn't always true, so we said, when is it true? So sometimes we say, when is it true? This one is a tricky one because it is true half the time and it's false half the time, and we can easily identify. All right, this is not something that gives people trouble in general, but the one common error, looking at 27, the one common error that I do see is that we get the remainder part incorrect when we use a negative. What was the rules on the remainder?
Has to be positive.
Well, not negative, but is there a range?
Greater than or equal to 0, but less than the divisor.
Yes, it's between 0 and 1 less than the divisor. What is wrong is there anything wrong with me saying negative 13 equals 3 times 3 minus 22? Is there anything wrong with that? No, then I'd be saying my div is 3 and my mod is negative 22. But could I also say that negative 13 is 4 times negative 3 minus 1? Here's the problem. If I can state this over and over again, I can use an infinite number of statements that are all true, all of them having a different remainder. We agree that div and mod are functions, and I can only get one. Oh, so it's not the div that determines it, it's the mod. I can answer this in an infinite number of ways. Again, I'll go back to 5 goes into 20 4 times. It goes into 23 times with a remainder of 5. How about it goes into 25 times with a remainder of negative 5? Could I do this all day? Forever, ever, never? Yeah. But let's just stick with it goes in exactly 4 times with 0 remainder, because the remainder has to be a number between 0 and 4 if I'm saying I'm dividing by 5. If we agree that the remainder is limited, then it automatically means there's one remainder and there's one div. But if I allow my remainder to be anything, particularly negative number, that means there's an infinite number of answers to every question. And that's where we get into trouble, okay? So when I'm looking at this, well, negative 13 divided by 3, isn't that just going to be negative 4 minus a third? No, it's negative 5 plus 2/3. That's how we have to answer it, right? Does that make sense? And if I don't remember that, I'm going to get into trouble. Oops, hold on. Now, contradiction. I want to show that for any even number, which is equivalent to saying every even number, this is not divisible by 4. Do we agree with that statement? Because n squared, if n is even, n squared is even, and I'm adding 3, clearly that's going to be odd. I believe it's true. You got to start there. Do you believe the statement's true? You're supposed to, yeah, I believe it's true. Yeah. If I had said n squared plus an even number, that changes things, doesn't it? That maybe it's true, maybe it's not true, I don't know. I believe that's That statement is never divisible by 4. So how do I prove that? That it's never divisible by 4?
You assume that it's.
Do I assume it's always divisible by 4? No.
There's at least.
The negation of always not is at least one time it is. And so that's how I do this contradiction. I say, let's suppose there is a number out there that it works. Let's suppose there is a value of k where that's true. And then what do we got? We have an integer on the left equals a fraction on the right. We have a contradiction. So I'm going to change this question to plus 4. And I'd say, is this true or false? N is an even number, n is an even integer, and now we're going to go plus 4. That's always true.
Well, it says not divisible.
No, but I'm saying it's always divisible by 4.
Yeah,
What
so
if it's
saying
n
not-
squared? What if it's n squared plus 2? Start thinking of n's. 2 squared is 4 plus 2 is 6. 4 squared plus 2 is 18. 6 squared plus 2 is 38. Those are not divisible by 4, are they? Oh, so a good question would also be make it n squared plus 2 and show it's not divisible by 4. Because at first you'd say, well, it's an even number and I'm adding an even number. It's still even, but it's not divisible by 4. So the way we attack this one, again, proof by contradiction, I assume it's true at least once. Where's my contradiction? It's the 3/4 part. It's that I said an integer equals 3/4, but 3/4 is not an integer. So I've got 3/4 is an integer and 3/4 is not an integer. I know it's not. There's my contradiction. So my original assumption that there is a case is incorrect. So that means there is no case. That is always not divisible by 4. Let's see, is that? Okay. Now, any question on any of these problems? Hopefully you had time to look at them, and if not, certainly get to them by the weekend.
On what page was the 2.1 chart?
What version do you have?
The online.
If you're in the fourth edition, it's page 35. It's big and blue. Now, let's go back to what can you bring? In every math class I teach, I always allow people to bring certain things. Any theorem, formula, or definition that we've done in this class. Not examples, not how-tos, but in this class, have we done a lot of vocab? Have we got a lot of theorems? Have we got definitions? Yeah. Your formula card is probably nothing but. Do we have formulas, per se? You know, the Gram-Schmidt orthonormalization process, very specific formula, right? Coming up with the linear regression using matrix multiplication, right? X transpose X inverse X transpose Y. That's a formula. That's powerful stuff. That's stuff you wrote down. But in linear algebra, when you got to the end, your card was mostly things like, what's the meaning of one-to-one, onto, kernel, range, rank, isomorphism, right? Because these are all brand new terms. That was far more important than formulas. So in this class, there is language that we have done. So something like, has anybody ever seen this in a different class? It's unlikely. What class would
I
you
saw it
see?
in statistics when we're doing probability for whatever reason.
Okay, that's a different-
given B.
Right, and that's a different use of that bar. That bar means A given B in a conditional probability
Yeah, it
case,
confused me.
which is very confusing. But that's a different, in statistics, we would write it this way. The probability of A given B. So in statistics, that vertical bar has a very specific meaning unrelated to divisibility. But divisibility is brand new. So I would probably write something like this. A divided by B means that what? B equals, you know, Ka, right? Something like that. That's what it means. That addition and multiplication of integers is closed. That's the only one we assume. Everything above it, remember our number group? Everything above the integers, rationals, irrationals, reals, those have to be proved. But the integers I get to assume. Because the other ones I couldn't prove that, but I can prove the rationals, things of that nature. Anything that you're looking at, now what a lot of folks do in the next few days, they'll make something, they'll take a picture and say, hey, is this legal? If it's an example, if you're using an actual specific problem, no, that's not legal, because that's open book at that point, okay? So you can't write how to do a proof, but if you've done a few, you know what's going on.
Can I write the definition of a rational number? Or
Sure.
something akin to
But, for example, unless you know these, I'm going to give you a problem and say, tell me, do the algebra, give the reasoning. Okay, that's, I used the distributive property. That's the identity law. You did this on a quiz, and almost everybody got 100% on that. You say, well, it's easy because I got to look up the reasons. You're right. Well, I'm saying write down the reasons, because unless you know that, I doubt anybody here knows that. You can all use it correctly, but do you know all of them? Probably not. I don't need you to know all of them. I need you to be aware of them and how to use them. Okay, so which one did I do? That looks like the idempotent. Oh, that looks like the distributive law. Okay. Because you're going to say this is true because. You can make an argument, one of the most important. What are these results called? De Morgan's laws. These are critical. Anybody who's done programming understands that we know what the answer is, but it wouldn't hurt to write it down, because what's the only error I'm going to make here?
Changing the word and.
That's a critical error. Do you agree? So I would just say, something like that. Keep it really, really simple. And when you're writing down formulas and things like that, I would just keep it P and Q. Don't write statements. You can always convert words into P's and Q's, but write down rules like that. Everything I'm going to ask you, you've already done. There's nothing I'm going to ask you that you haven't already done. And most everything we've done as a group, we've done really, really well. But quizzes, careful. Quizzes are on one lecture. They're open book. You have a few days to do them. You're supposed to get the quizzes right. In an exam, it's everything at once. It's a different animal altogether, and the problems are just random. I put problems really to make them fit on a page conveniently. So it's not like page 1 is just going to be lecture 1, page 2 is lecture 2. No, everything's all over the map.
How many questions is on this?
I don't know, 30 something.
Okay.
But some of there are questions that are 10-second questions. In fact, I would say half of the test, it can't take 15 minutes. It can't. There's just no way. But if it's a truth table, that's going to take a lot longer. If you're writing a proof, that's going to take a little longer. But have you had proofs where you wrote them at light speed and just got done really quickly? Yeah. So the proofs are all going to be short. If you look at my answer keys, the proofs generally, I don't have a lot of writing. There's not a lot to say. Sometimes we go around in circles. Now I'm going to remind you of this. Most of you have been in my classes before, and I like to give you more questions than you have to do, because I'm saying, hey, show off. I know how to do this one. I'm going to write a great answer. I know how to do all of them, but I'm going to take the ones that I can write the best answers for. That's kind of my attitude. I'm going to assume you can do all of them. Show off your best answers you can give. Now, you answered everything on the test. You double-checked. Since there's no arithmetic, the double check should be pretty easy, right? I can't make an arithmetic error if there's no arithmetic except on the div and mod, perhaps. All right, I did my proofs. There's still 20, 30 minutes left in the class. What do? Do an extra one, right? That's called insurance. I'm asking you to do 3. If you have time, you should definitely do 4. Why? Because you might have messed one of them up. Now, will the 4th one count? Again, most of you have been in my classes before. Does the insurance ever actually count? Pretty much never. Why? There's a reason you didn't do it in the first round. There's a reason you put it off till the last one, because you had less confidence. Often the case. But others of you go, no, I can do every problem. So I just did the first 3 proofs because I can do all of them. Okay, insurance, okay, I did the first 4. Don't do all 6. You're cutting into your time to check. Will somebody do all 6? Yeah. Everybody does this. On the Calc 2, the first exam, I will give 14 questions always. And I'll say do 10. And most of them are integrations, because it's methods of integration. The other ones will be the applications, work, fluid force, that thing. And then I'll throw an extra credit question on there. And they have to do 10. And I'll say, if you're smart, you're going to do 11. And do the extra credit. So what happens every Calc 1, Calc 2 exam, every single student does all 14. Every single semester. And half of them don't get to the extra credit, which is just knuckleheadish. I said 14 questions, 10 are going to count. Why are you doing all 14? 4 of them are not going to count, and you didn't leave yourself time. I always throw an extra credit question on every exam. An extra credit is an over and above challenge from the same material, like your bonus questions on the quizzes. Extra credit is not just, I found some really cool problem on the internet to see if I can stump you, there's your extra credit. That doesn't make any sense. No, it's something we've already done, but a little extra challenge. So it might be a fairly difficult You know, maybe it's one of the ones where you have to give all the reasons and show it's a logical equivalent. You know, something where there's some work involved, but you already know how to do it. But here's how you want to take your test. Do everything other than the proofs, double check yourself. Get 3 proofs in there, write them really well. There's still time on the clock. Do the extra credit first. There's still time on the clock. Okay, now go back and do an insurance problem. The insurance isn't going to count, but if you messed up one of the other ones, it would replace it. It's your best 3, no question. But if you do an insurance problem in lieu of the extra credit, you're not getting extra points. You understand? The extra credit is frosting. It's not all or nothing, because the problem itself might be fairly lengthy. It's, did you do it mostly right? A lot of us here have messed up things, let's say on the truth table. We messed something up. We got an incorrect conclusion because, you know, we missed a T or an F, but your big picture was good and your conclusion was based on your truth table, so at least you did that part correctly. You just had an error in the truth table. I didn't give you 0 on the problem. You didn't get full credit because it's not a correct answer, but you demonstrated correct understanding. That's how things work with partial credit. If you demonstrated correct understanding. Now, this is a killer. If I miss this and I have the wrong thing, then it doesn't matter what I write after. It's a completely different problem. So you've got to be very careful on things like that. That's your arithmetic, if you will. Okay, that's your arithmetic check. Did I distribute a negative correctly? When I'm giving a negation of a statement, did I negate a for all and give another for all? You know, I mean, can you write things like that? You know, sure. Yeah, that's a theorem. It's stuff we've done. We proved this, by the way, using truth tables and stuff. So, 3x5 card. As long as you don't write astronomically large, it should be really easy to fit everything you need on both sides of a 3x5 card. Most of you make the same mistake every semester. You do your micro writing, because I need a lot of space, and then you used 1/4 of one side of your 3x5 card because you thought you were going to use all of it, and you didn't, and you can't read it. Some of you know exactly what I'm talking about because you do that every test. You write too small. No, write everything you think you're going to need on a piece of paper. Now transfer it to the formula card. And what a lot of you do, I don't need anybody to do it on a computer. But every semester, some people will do it on their computer, and then they just shrink it down. The smart way to do it, if you don't want to do that, is write big and legibly, and then put it on a copy machine and shrink it down. Now it's small, but it's still easily read. If you simply write really small, it's hard to read. And by the way, only shrink it down if you actually have a lot of stuff that you don't think you can fit on there. It's unlikely you're going to run out of room, unless, like I said, unless you write really big. Okay? So, even though we meet every day at light speed, the placement of the exam is quite fortunate for you guys. We actually have, 5 more days until the exam, and we finished the material 2 days ago. That's actually almost as long as you'd have during a normal semester to prepare. So this is a good thing. I don't want to hear you spent all weekend reviewing, but you probably want to spend a few hours, certainly this weekend, reviewing. And Monday is a holiday. It's an odd holiday because it's not a holiday that is observed by everybody. And it's not a holiday that is observed by all schools yet. I'm kind of hoping, since we made it a holiday, I'm kind of hoping we start treating it seriously now. And what I mean by that is, I know people that have businesses. I know people, there's no holiday. Why would I give my people a day off? Well, I'm giving a 4th of July off. Yeah, it is a federal holiday, but it's one of those, again, that hasn't quite stuck yet. I'm not sure why. Maybe it's because, and again, this is my own personal opinion, this is a holiday that should have been over 100 years ago. And regardless of your opinion, this is considered one of the most important events in American history. And we just decided last year for the first time to acknowledge it. It's been in the works for generations of whether we should acknowledge it or not. And the reason I'm bringing it up is because I've talked to many educated adults who have absolutely no idea what it is we're acknowledging on Monday. And I'm sorry, but if you don't know it, it's kind of embarrassing. Does anybody want to offer what's we're acknowledging on Monday?
It's Juneteenth, right?
Yeah, but what are we observing?
End of slavery.
The end of slavery in the United States. I don't know about you guys, but I think that's kind of a big deal. And why did it take this long, over 150 years? But we're doing it, and this is the problem. Most Americans don't even know what it is, and they, or you can look it up. right, let's go ahead and stop. I'm gonna turn this off. Monday.